Hi, this is the second part in our Why Measure Why EBTRON presentation series. Basically what we're going to do today, of the 5 items we discussed briefly in the last presentation, today we are going to speak about the indoor air quality portion. Okay, so this is a little bit longer than the last one, but it covers a lot more information. All right, so we're just going to step right into that now. No matter how you slice it, okay, indoor air quality is driven around one of the paramount things that you have to do for indoor air quality is to provide proper dilution ventilation. Now, folks are trying to come up with ways to reduce the amount of outdoor air that we need. I don't know if I agree with that because I honestly don't think we provide enough to start with. But the bottom line here is we need to provide adequate dilution ventilation, and every current standard we have, whether it's on the healthcare side or the non-healthcare side, is based on providing ventilation rates, okay? So that's basically, one of the things that we want to make sure that we drive home today. All right, so let's just take a look at this real simple diagram. And this is an occupied ventilation zone, and it doesn't matter to me where what the contaminant source is, as long as it's sourced from within the space. Okay, if there was no outdoor air coming into that space or no filtration that could remove the contaminant of concern, basically what would happen is the contaminants would build up, and we get to a point where the contaminant level exceeded a threshold level, and it became, a space that we wouldn't want to be in, a fairly dangerous space. And so how we deal with that, and how we've dealt with that in healthcare, and it's clear in healthcare, okay, we do basically a combination of targeted high-level filtration and outdoor air, okay? And if you look at healthcare, it's basically room air changes. Room air changes are based on, how many times the air passes the targeted filtration filter, and outdoor air changes, how many times are you replacing the air, okay? And that's really what it comes down to. You have to do a combination of both to keep the pollutants and contaminants below your threshold level. And you may do other things. I'm okay if you want to add devices that maybe improve the way your filtration works, and I'm okay if you want to add something like UV lighting to if you have viruses and things like that. I don't really have a problem with that. I do have a little bit of a problem with reducing outdoor air. Actually, I have a big problem with it, but that's a whole nother story, and I'm not going to go into that today. It's just we have to do a combination of these two things. These are the primary things that we're going to do, okay? And a lot of times people try to, they go out of their way to avoid outdoor air because outdoor is expensive to condition, but the bottom line is we need it, okay? And so when we talk about outdoor air, all right, I'm not going to talk about filtration or anything else. I'm going to talk about outdoor air because that's what we do, all right? I'm going to start off with a paper that we wrote back in 1990 that was, a pretty important paper, and it's pretty amazing to me that I'm still able to use, this paper today to talk to people, over 30 years later, okay? And the primary author here, I have to give Mr. Solberg credit. He's the person who put this together, and Len Damiano and myself at the time, I say we went along for the ride. It was a long time ago for me, okay? But it's a very important paper. It's very important to understand it, okay? And it's simple. I've kind of changed some things up in it over the years and to make it as simple as I can, okay? I like simple because, we can complicate things to the point where nobody really understands it. But if we keep it simple, all right, then you can draw your own conclusions and bring it to other people that may not understand it as well as you do, so that they can understand why we have to do some of these things. So we start off with fixed minimum position intake dampers and why they're a problem, and particularly why they're a problem on VAV and multi-speed fan systems, okay? And it's real simple. I mean, if you look at that lower right-hand part of the slide there, you know, I have a louver and I have a fixed damper. So it's a fixed orifice, right? So what ends up happening is I have a certain pressure drop across it that's associated with the supply fan volume of air, okay? And if we reduce the supply airflow volume, and what will happen is the mixed air plenum pressure will drop with it, and the airflow will reduce because it's a fixed orifice and the pressure changed, okay, the pressure dropped. All right, and it ends up that relationship is linear, okay? It's proportional to the supply airflow rate. And so I like to look at a simple example here where we look at the combined louver damper pressure drop at design flow, design supply flow, and design outdoor airflow. And we're going to say that there's a 3/10 of an inch drop across it. So the mixing box had to be negative 3/10 of an inch to bring in the outdoor air that we wanted. Well, it ends up, if we reduce that supply fan flow, whether it be VAV or multi-speed constant volume, fan coil, any of those that changes speed, okay, what you'll end up having is that mixed air plenum pressure will change. And in this case, that mixed air plenum pressure changed about 2/10 of an inch. Not exactly 2/10, but for this conversation, 2/10 is good enough, okay, as the supply airflow dropped, okay? And if you look at the corresponding outdoor air intake flow rate that went along with that, it's linearly proportional. So basically a 40% drop in the supply airflow would result in a 40% drop in the outside airflow, okay? Which is a pretty big problem, okay? And so you look at these two things here and you say, okay, well, I have this, in this example, I have 2/10 of an inch change in pressure resulted in a 40% change in airflow. And the reason that we do this example is not because folks don't understand that supply flow changes affect intake flow changes. It's because we want to look at what else might cause a problem that I don't think enough people do look at, okay? And here what we have is a case where we're going to keep the supply flow constant, but something on the outside of the building, on the louver side, is going to make that same change in pressure, that same 2/10 of an inch change in pressure. Since it's a fixed orifice, it doesn't matter what side. If the pressure drop changes, the pressure drop changes, okay? So the flow is going to change proportionally with it. All right, and so when we take a look at this example that we had, where this 2/10 of an inch reduction in the mixed air plenum pressure was a 40% reduction in flow, now if we kept the fan speed constant and simply changed the wind speed and direction on the exterior side of the louver, we'd have a very similar situation. In fact, the example here shows if we go from an 18-mile-an-hour direct wind, which is a positive pressure on the intake system, to an 18-mile-an-hour crosswind, which is a negative pressure on the intake system, we see about a 2/10 of an inch change in that overall pressure, and that would also result in about this 40% change in the airflow, outside airflow rate. And that doesn't seem to be taken into account enough, okay? We see a lot of documentation out there. Standard 62 particularly talks about, making sure that you handle changes in fan speed, and you have to do some kind of dynamic control to do that. But very rarely do we see anything that says, hey, wind pressure is a problem. And it is a huge problem. If you take a look at this graph, I mean, basically the 40% variation is at 100% supply airflow, okay? So that on the very right-hand side of this graph, okay? The set point's that black dashed line, okay? And so what happens here is now you superimpose direct wind and crosswind and change fan speed, and you can be anywhere between those two red curves, and that's a serious problem, okay? And so, we're nowhere near our set point. So we're using, whenever we're using fixed dampers, particularly on recirculating air handling units that are exposed to wind pressure, these become very large problems that we have to compensate for. And then we actually had some data from our facility where we set it up one day when there was no wind, and we have, wind speed and direction outside on our building. And, we saw a day when, oh, well, we had this 15-mile-an-hour crosswind coming down the side of the building. So we took the data again. And what you see is the black dashed line is the data when there was no wind, and the red solid line is the average of the data when we had this crosswind. And I'm not going to get into it now because I don't have the time, but the scatter is actually the instantaneous readings of the flow meter, because it's showing the fact that you have to look at outside air intakes are a little different than anything else, actually, because you have wind speed that varies and you have direction that varies. It's not like when you say there's a 15-mile-an-hour crosswind down the side of the building, it might be 15 mile an hour straight down the side of the building. It could be 18 at a different angle to the building. It could be 12. And you get these gusts. And as you get these gusts across this fixed orifice, you get these small changes in airflow that you pick up with the airflow meter. Okay. And basically, we have to be able to make sure that when we're doing control, that we don't get too aggressive with the output of our control loop, because if we do, we'll just sit there and hunt. And that's a completely different conversation than I want to have today. The one that I want to really point out is, look, the black dashed line is no wind. The red line was a 15-mile-an-hour crosswind. It backs up what we're talking about, okay? Then the other thing you have to think about is stack effect. And most people think about stack effect and how it affects individual floor pressures. But it also affects how much outdoor air you're bringing in. In this case, you talk about simple picture, it's pretty simple. In this case, we have an air handler on the roof, and it's only serving the first floor. And so what you see there vertically is just my return duct. I'm not showing the supply duct or anything else. And I just want to point out that on a day when there's no stack effect, meaning that the indoor and outdoor temperatures are about the same, this is not a big issue. But when we get into the winter, okay, we have our column of air outside the building is much more dense than our column of air inside the building. So it puts a positive pressure on the downstream. In this example, it puts a positive pressure on the downstream side of that intake system, okay, which is going to reduce the amount of outdoor air that comes in if it's simply a fixed position or multiple fixed position dampers. Okay, so it's something you need to understand. The same thing is true in the summer, although the offset in temperature in the summer is generally not as bad as the offset in temperature in the winter. Okay, it just depends on where you are. And to carry this whole 0.2 of an inch thing through, basically, if we live in an area where there's a 100-degree swing in temperature on a 70-foot low rise, so this is like a 5-story building, you get that same 0.2 of an inch. And if you're in climates where the temperature variation is a little bit different, well, you just have to make some adjustments to the height of the building to have the same problem. But the point here is, it's not just high rises. All right, this is a big problem that we have to compensate for. All right, so stack pressure is a big deal too. And when you take a look at the going from winter to summer stack, it's a very large problem. Again, that 40% swing and flow was at design or 100% supply airflow. So that's a constant volume system. But the others now, as we have, multi-speed fan systems, VAV, it gets even worse, okay, as we turn down. And of course, the reality of this is that you don't just have wind or stack, you have a combination of the two. And when you take a look at it that way, you realize that if you just rely on fixed damper positions or even multiple fixed damper positions, okay, which I'm going to actually show you why that's even worse, you don't really know how much outdoor air you have coming in. and it amazes me, all the things that I see people doing today. Oh, we're trying to reduce outdoor air and we're trying to do this. That's fine but you still have to measure it and you still have to control it, because you can't have this kind of variability or variation in intake flow rates going on. It's not this magic number that you set and forget. It doesn't work that way. Even for the folks that are advocates of reducing outdoor air, whatever they are, they reduce that. They say, oh, we're going to reduce the outdoor air. But I never hear anybody talk about, well, we have to measure and control it, or rarely. It doesn't matter. We have to measure and control it to compensate for these system changes, right? And then a lot of times we'll see people do two position. Now I'm doing two position here where I'm resetting the outside air damper with the supply airflow. Some people do that to compensate for fan speed variations because it's very inexpensive. Okay, now it's not an exact analogy, but also folks do this for DCV, set min and min max flow rates. But what I want you to get out of this is you've got to understand where the problem lies here. Okay, first of all, everybody assumes when they're doing this that the damper is linear, and the damper is not linear, but that's the least of my worries. What happens is when we're at this particular condition, which is design airflow, to get in the outside airflow, the damper is in a fairly, in a more closed position than it will be when we reduce the supply flow. So whenever you go multiple positions on a damper like this, if you go to a more open position, it's kind of exactly the opposite on a DCV system. But as you go to a more open position, you've changed the flow coefficient of this damper and of this intake system. And basically everything I've been doing is based on the flow coefficient of the intake system. Okay, so when you go to a more open damper position, you've got less resistance to flow. So a given change in pressure on the exterior of this building is going to result in a larger change in flow. And that's what I'm just showing you here. Even if the damper was linear, which is what I'm assuming, it really isn't. Okay, what happens now is in this case where you're opening the damper to compensate for supply airflow changes, you've really reduced the resistance of that intake system. So a given wind pressure is going to be a greater change in flow. And that's what I'm showing you here, okay? And then I do the same thing with stack effect, okay? It's a bigger problem. And when I combine them two, you really don't know where you're at. And it's why we end up, you think about all these buildings that are relying on these fixed damper positions. You have these facility managers that they don't, never mind the facility managers, even those of you that are engineers don't understand these effects, and you're like, oh my gosh, I can't control the outside air, and a lot of facility people end up closing their outside air intakes because they're like, I can't, my building is out of control. I'm either not bringing enough outdoor air, pressurization problems, which that didn't go away when you close them, or more likely, we're bringing in too much outside air, we can't condition the air, we have freeze problems, whatever it is, you're going to have all these issues because you have completely uncontrolled outdoor air. And then, it's like, oh, give up, Dave, but no, there's even more problems here, because whenever we're using dampers to control flow rates, we have damper-induced problems. And there's three of them. There's hysteresis, there's binding, and there's deterioration. Okay? And hysteresis basically is the slop in the damper. You can take the drive shaft back to the same position, but the linkage has enough slop in all dampers to make the damper blades not come back to the same exact position. Binding typically happens with age, although I have seen dampers right out of the box bind. And deterioration, again, typically happens with age, meaning that the damper seals are deteriorating. All of these things affect, for a given shaft position, what the blade position is, which affects the flow. The only thing I'm going to really show you here, this is from our building with a very high quality damper. Okay, and all we did is we went from night setback mode to 15% open. or we went from 100% economizer to 15% open, and we measured the outside airflow rate with everything else being constant. Okay, and what you see there is the red data set was from economizer to 15% open, and the blue data set is from night setback to 15% open. And depending on which direction we came from, we have a 20% variability in the outside airflow rate. So which one is the one that you should have set it up for? And the answer is that there is no right way, okay? Dampers have hysteresis. So when you take a look at this whole deal, all right, you see that the factors that influence these outside air intake flow rates are significant. We have system effects, which are primarily fan speed variations. We have environmental effects, which are wind pressure and stack pressure. And we have damper issues, which are hysteresis, binding, and deterioration. And honestly, when you look at these, and I'm being nice, a fixed damper system, okay, if you're within 50% of your desired set point, you're having a good day. And I always say, that's not a good day. And honestly, the errors are even higher than that. So you have system after system out there that has problems. And it's not just recirculating air systems. I mean, we have these wind pressure problems and stack pressure problems on DOAS. We have filter loading on DOAS. We have, basically DOAS systems serving, multi-speed fan coils in some cases. I just use this because this is the worst case. And, I want to just point out that you have to somehow control outdoor airflow rates. All right. And so at this point, what I ask people to do, I kind of step through my arguments. So my first argument that I did real quickly, okay, was that dilution ventilation is paramount to IAQ. All right, you have to dilute contaminants. I agree that high-level filtration is extremely important and needs to be there. Particularly in our non-healthcare facilities where it's been kind of non-existent for years. We have to figure out how we're going to deal with that, okay? We didn't talk about how the air is distributed within the ventilation zone because that's extremely important too. But, to me, you have to measure these outdoor airflow rates, all right? And you have to really control them. It's not just measure them. And it's not on just large VAV systems, it's on everything, okay? And, that's what I want you to get out of this, okay? Now, at this point, I don't think I've made any arguments as to how you should determine the airflow rates. But you do need to determine them, okay? You need to know how much outside air is coming in, and you're going to need to control that. Okay, thanks for attending. If you have any questions, feel free to ask them. We'll see you in the next time, okay? Bye.